We will soon see examples of C functions and assembler code for power. But first we will mention what is called function call conventions. And when a compiler produces machine code for a function call, it must take into account where are parameters passed and the return value, and what should the call frame look like. This is documented for each platform, and the platform is a combination of processor and operating system. So although there are both Mac OS and Linux for power machine, there was Mac OS until year 2005. Even though they used identical hardware, there were some minor differences in the call conventions. But usually most of it is the same. Okay, so what does the call conventions for power look like? Well, we will not go into all details. It's many pages, but some interesting things. Okay, so it's R1, which is the stack pointer, and this register must always be a multiple of 16 bytes. One can use the stack pointer and trace all the calls that have been done since main, and as a linked list. And this is done, for instance, by debuggers. Okay. Some registers are allowed to be destroyed by the call function. And those include those registers in which parameters are passed. These are called caller save registers. Because if the caller, the one which does the function call, wants to preserve the value, it has to save it before doing the call and then restore it afterwards. And the other registers are called callee save registers. So there are two groups of registers. And when the compiler decides which register a certain local variable should be put in, then it takes into account whether this variable is used before and after function calls. Okay, return values are passed in the same register as the first parameter. Well, the integer parameters are passed in these registers. And if there are more parameters, then they are passed on the stack. Actually, in the caller's stack frame. But that's not very important to know unless you write the compiler for power. Okay, let's go on with machine code. So this function is quite trivial, and it's very trivial, and we should maybe expect that it's just a few instructions, such as only 2 instructions. One to add and one to return. We don't need to save the stack pointer, the return address, but actually there is one more thing that we need to do. But let's first look at this code. It's the unoptimized code, and it looks terrible. So what is happening? Well, first I will not go through everything, but the call frame is set up, and the parameters, they are passed in register 3 and 4. They are moved to register 9 and 0, and then they are saved, and then they are loaded, and then they are added, and then there is something called extend sign word, and that means copying the most significant bit in an int into the rest of this register. so that it has the same value. I mean, it has the correct value when put in a 64-bit register. Okay, and then it moves this value into the return register, and then it restores the frame pointer and loads this that was saved before, and then returns. As we can see, most of this is quite redundant, and therefore using optimization is a good idea. Here there is a 64-bit add, but note the int is only 32 bits. So therefore only the 32 bits, lower 32 bits of the 64 bits must be used, and therefore sign extension is used to copy bit 32 into all positions to the left of this, and then we return. I described sign extension before when I took -8 in 4 bits and put the same value in 6 bits instead. Okay, adding to 64-bit integers. Then what happens is that we simply add the two parameters and return. So we put the return value into this register at once and then return. If we instead have 32-bit mode, that means we are not allowed to exploit all the 64 bits of a register. Some power machines are, I mean the chip, don't have 64-bit registers, but only 32-bit registers. And we can create programs on a 64-bit machine with this mode and run them on a 32-bit machine. So what we have to do then is to add this in 2 steps. So first we add, well, first of all, the first parameter is put in 2 registers, in register 3 and register 4. Each register is 32 bits. So the value of A is this, and the value of B is this. So the first thing that we do is to add R4 and R6. That's done here. And this C says that we should notice if there is a carry out from this. A carry is that the value results in a 1 which doesn't fit in the 32 bits. Okay, then we add that carry, if there was one, when we add R3 and R5. So now we have computed the 64-bit sum. And then these are moved to 3 and 4, and then it's we return. Okay, let's look at the while loop instead. So say we want to perform this, and if we look at this part, we move the number of iterations into this counter register, and the number of iterations, that is n, and here we copied n into register 3, and this dot means setting bits telling if this is a positive, negative, or equal to 0. Okay, we'll come to why we do that later. But suppose we want to do this loop. Then we have saved the number of iterations in the count register and perform what we should, and we decrement this count register and move to this place if the count register has not reached 0. When it has reached 0, we just return. Okay, that's fine. But say n is negative. then we should not iterate at all. So what this code does is to do a conditional return. So when it moved n from register 3 to register 0, it checked if it's positive, negative or 0, and it remembers that until the next instruction, which has a dot. An instruction with a dot sets these bits. Okay, but here they don't use it, so we can do a conditional branch. That means branch less than equal to the contents of the link register. That means return. Okay.